All right, so on the last slide, we were just discussing what work you need to show for the AP exam. So given the below table, we're going to just take a look at the question we answered previously. What's the probability that a randomly selected household with a landline also has a cell phone? So just keep in mind this is a little bit tricky, that a randomly selected household with a landline, that's kind of your given. That's your given statement. We know that it has a landline, so think about what you're given first. Also has a cell phone. That was just, we're going to be coming back to that later. So we're finding the probability that they have a cell phone given that they had a landline. And just notice in the question, it doesn't say like given that they have a landline. You have to really think about what you're given first. What's the probability that a randomly selected household with a landline, since it says with a landline, that's kind of our key statement, and knowing that that's what your given portion is, also has a cell phone. All right, so once we identify our probability, we're going to use our conditional probability formula, cell phone, given they have a landline, the fact that they both occur over what's given, just the landline. All right, and the important parts to show are 1, this probability statement, 2, this fraction, cell phone and a landline, right here, divided by the probability that it is a landline over 0.60 in the denominator. So yes, these are yucky decimals, but even though they're yucky decimals, you want to still sort of show those in your fractions. This is probably the only math class where they'll have you do that, and then your final decimal answer. Don't leave this as your answer. Get the actual probability. Okay, so what works needs to be shown? Your probability formula with correct notation, the fraction with the decimals filled in, and then your decimal answer. All right, so we briefly talked about the last question, and it said like it doesn't state given that you have a landline. The question is not always going to state given that you have a landline, what's the probability that you also have a cell phone. So it's never going to be quite that easy. Here are some other words to look for in order to recognize that you're dealing with a conditional probability question. So if it says like who has a landline, whose has a landline, which houses have a landline, if it has a landline, and those are all your those are sort of your indicators that it's a conditional probability, and that's going to be what's given first. And then the obvious one is given that you have a landline. So be on the lookout for those words and understanding that when you see them, that means that that's a conditional probability. All right, so what happens if we're not given a table? How can we find the probability of A and B occurring? The probability that events A and B both occur can be found using the general multiplication rule. So the probability of A and B is the probability of A times, you're used to seeing the probability of B, so just the two of those together. Remember, that's only if they're independent events, times the probability of B given that A has occurred, where B given A is the conditional probability that event B occurs given that A has already occurred. All right, so honestly keep in mind that you're going to be using tree diagrams to do this. So just keep in mind that the AND rule is really just a multiplication rule, and most of the time this given portion is sort of going to be taken care of in your tree diagram. All right, so in other words, this rule says that for both of two events to occur, the first one must occur. Then, given that the first one has already occurred, the second must occur. And that means that these are not necessarily independent events. So you might be saying to yourself, hey, wait a second, this formula looks pretty familiar. This formula is not on the AP formula sheet. However, think about your conditional probability formula. If I rearrange this and put the probability of A under there, then, okay, rearranging again gives me my AND probability. So if I divide by the probability of A, that's your conditional formula in your formula sheet. Then when I multiply probability of A back out, right, that gives me my AND formula. It's the general multiplication rule. It's just the conditional formula rearranged. All right, so go ahead and try this one and think about what work you're going to need to show for the AP exam. About 55% of high school students participate in a school athletic team at some level, and 5% of these athletes go on to play on a college team in the NCAA. So the question is, what percent of high school students play a sport in high school and go on to play a sport in the NCAA? All right, so go ahead and try it before you check your answer on the next slide. All right, so let's see what work we need to show for this question. So here's what we know. Well, the probability that they're in high school and that they're going to play for the NCAA, using our rule from the previous page, is the probability that they played a sport in high school times the probability that they play for the NCAA given that they played in high school. So we're only looking at the students that played in high school to get chosen to play in the NCAA. All right, so we know that the probability of doing the high school is 0.55 of playing in high school. The probability that you played in high school, or sorry, played for the NCAA given that you already played the sport in high school is 0.05. This is all given in the problem. So multiplying those two together, you get 0.0275. Okay, because that probability was given to you. So you have to recognize that that 0.05 is the probability that they played in the NCAA given that they played in high school. Okay, so the work highlighted in yellow is what you'll need to show for the AP exam. The probability statement, your work, and then your final answer. Okay, so we briefly talked about in the last slide that the conditional probability, when we multiply two events, we have to use the conditional probability, but sometimes we don't have to, and that is when the events are independent. So when the knowledge that one event has happened does not change the likelihood that the other event will happen, we say that these two events are independent. So for example, if we're talking about what's the probability that it's Sunday and that it rains? Well, probability of it being Sunday is not going to affect whether or not it's going to rain, and the probability that it's going to rain is not going to be determined by the day of the week. So those two events are independent. So what does that look like? So two events, A and B, are independent if the occurrence of one event does not change the probability that the other will happen. So the probability that it's Tuesday is not going to change the probability that it's going to rain. All right, so if two events are independent, let's look at this using our conditional probability formula. The probability of A given B is the same as the probability of A. So basically it's like saying the probability that it's Sunday given that it rains is just the probability that you get Sunday, because it's going to be Sunday 1/7 day of the week. The probability that raining is not going to change the day of the week. It has no effect on it. If we do the other way, the probability of B given A, if that's the same as the probability of B, that's like saying, okay, the probability that it's going to rain given that it's Thursday. Well, being Thursday isn't going to affect the weather. There's a lot of other things that go into the weather, so the probability it's going to rain is still going to stay the same, whether it's Thursday, Friday, Saturday, Sunday, Monday, Tuesday. So it's basically like saying the event that's occurred, the given event, has no effect on the event A or B that we're looking at. The events have no effect on each other. They're completely independent. So if this statement is true, then I know the two events are independent. So if they're independent, we can simplify the general multiplication rule just to be the probability of A and B is equal to the probability of A times the probability of B. We don't need to use that conditional formula for the second one because the two events don't affect each other, so B is not going to change whether or not A has occurred. All right, so there's two ways to prove that events are independent, and you will often be asked to do this on the AP exam. One, if we say that the probability of A given B is the same as A, so that's basically like saying B is not affecting A whatsoever, and the probability of B given A is the same as the probability of B, once again, basically like saying that A is not affecting B whatsoever. We're using the conditional probability formula to prove that these two events are independent. Well, why does that work? It proves that they're independent because it's basically like saying B is not affecting A and A is not affecting B. Since they're not affecting each other, therefore they're independent. Having one is not changing the probability of another. The other way to prove that they're independent is to find the probability of A and B. If the probability of A and B is the same as the probability of A times the probability of B, then the two events are independent. So if this equation is true, we can say they're independent. Most of the time you're going to be using way 1 to prove it, but way 2 does work sometimes. Okay. Now, how do you get credit for this? You must show the work plugged in. Don't just give the equation and state therefore they're independent. Like, don't just say this A and B is equal to probability A times the probability B. Well, did you actually check it? How do we know? That's incorrect. Remember that stats is all about proving where your information came from. You have to prove to the reader that you know what you're talking about and that you didn't just make this up out of thin air. All right, so you want to actually show what these numbers are. So you can just leave this like it is, show the numbers directly underneath it. If they're equal, independent, not equal, not independent. All right, so let's take a look at this next question and using the multiplication rule for independent events. So following the Space Shuttle Challenger disaster, it's interesting, if you have a second, go ahead and look it up. It was determined that the failure of O-ring joints in the shuttle's booster rockets was to blame. Under cold conditions, it was estimated that the probability that an O-ring joint would function properly was 0.977. Okay, that was the estimated probability. Go ahead and read on. Actually, this is just a really interesting tidbit of history to look up and read about. The disaster could have actually been prevented, and people said not to put the space shuttle up into space at this time because they didn't know enough about the probabilities of O-ring joint failures at the temperature was launched to actually launch it. Okay, so we're assuming, back to the problem, all O-ring joints succeed or fail independently. What's the probability that all 6 would function properly? All right, so each of them work independently. One working does not affect whether or not the other one is working. So this is like a giant independent question, a giant multiplication rule. So it's saying that the probability of joint 1 is okay, and joint 2, and joint 3, and joint 4, and joint 5, and joint 6. It's a giant independent multiplication rule. So we're basically finding the probability of joint 1 plus the probability of joint 2 times the probability of joint 3 times joint 4 times joint 5 times joint 6, which are all the same in this case, which is 0.87. So the probability that they would function properly is 87%. All right, it's a little crazy to think about putting your life on the line at 87%. You want it to be 100%, right? All right, so there's an 87% chance that the shuttle would launch safely under similar conditions and a 13% chance that it won't. Would you take that chance or not? All right, so the general multiplication rule is especially useful when a chance process involves a sequence of outcomes. This is where we're going to use the tree diagram. Honestly, unless the probability statements are in decimals and are very clearly an and probability is given to you where you can create a Venn diagram, just get used to making tree diagrams. Let's take a look at what this looks like. The better you get at tree diagrams, the easier the questions will be, the less that you'll miss on the AP exam. What is the probability of getting 2 heads? So let's think about our sample space. We're flipping a coin twice. Our sample space, we can get heads, 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 tails, tails, heads, or tails, tails. The probability of getting 2 heads in a row is heads and heads, so 1/2 times 1/2, which gives me 1/4. I want to know, okay, so I can figure that out using the general multiplication rule. How can I do that using a tree diagram? So let's think about this. When I toss a coin, I have 2 choices. I can get heads or I can get tails. Tree diagrams always include the probabilities. The probability of getting heads is 1/2, the probability of getting tails is 1/2. This is just what my first toss represents. Then from this portion right here, if I get heads the second time, what is the possible scenario that could happen with my second toss? So with tree diagrams, you're sort of putting this in order. What can happen? What can happen first? What can happen second? So if I flip a coin the second time, I can get heads or tails again. So I can get heads, heads, or heads, tails. Heads, 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 tails. If I got tails the first time, on the second toss, I still have 2 options. I could get tails, heads. I could get tails, tails. Tails, heads, tails, tails. Okay, and you always want to include the probabilities associated with each event. 1/2 heads, 1/2 tails. The second time, 1/2 heads, 1/2 tails. 1/2 heads, 1/2 tails. Now, where did this 0.25 come from? It's the general multiplication rule where I'm multiplying across the tree diagram. So 1/2 times 1/2 gives me 1/4. 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 You always want to fill this in at the end of your tree diagrams because that's always going to give your and probability and just to make your questions so much easier. All right, so the last thing I want to take a look at in this slide is thinking about remembering the fact that the probability of the probability of any event occurring always adds up to 1. So if you want to do a double check, add up all the probabilities at the end of the branches. They should always add up to 1. Why? Well, the event, remember, a probability of an event occurring is always between 0 and 1. If these are the 4 in my sample space, the probability of each occurring added together has to give me 1 because it's 100% of my sample.